Everyone to the afternoon session. So first speaker for this afternoon is Johannes Carmesin from here in Cambridge, and he's going to tell us about infinite matroids.
Right, so this will be an introductory talk to infinite matroids, and I promise in the abstract that it will be self-contained. So if this is not the case, or if you have any other questions, then please do interrupt. Yeah, and I'm very happy that I have the opportunity to speak. And right, so the starting point of this talk is planar duality. Right, so a graph just consists of a set of vertices, and for any pair of vertices, either they're joined by an edge or they're not joined by an edge. And we start with G being the half grid. And then topologically, the dual of the half grid we get by putting a vertex of the dual graph into each face. And now we join two of the new vertices by an edge if the corresponding faces share an edge in the original graph. So the dual is something like the graph we started with, but with this additional vertex at the bottom, which is infinite degree. Right, so this is a topological way to explain what the dual of a graph is, but there is also a way to explain it completely in terms of linear algebra. And to explain this, Whitney in the 1930s introduced the cycle matroid of a graph G. And the cycle matroid of a graph G is given by the edge sets of the cycles of the graph. And the important thing to note here is that we only store the information for every cycle which edges appear on the cycle, but we do not store the information in which order they appear.
So it's just the union of the edge sets of the cycles?
Right, so matroid just consists of a ground set called the edge set together with a system of subsets, and these are just the edge sets of the cycles.
But what you wrote there, what do you mean by the edge set? The edge sets are the new vertices, or?
So matroid just has edges, right? So you completely forget about the vertices, and the cycle matroid of a graph is just a pair consisting of the ground set E together with the set curly C, where curly C is the set of those sets X, such that X is an edge set of a cycle.
I see. So it's a hypergraph. It's on E.
Yeah, you could think about it this way, but the point is really that you no longer just think about it in terms of graphs, but kind of in this context, and yeah.
Right. It's a set with a family of subsets.
Yeah.
That's a hypergraph.
Yeah. Right. Okay. So that's the cycle matroid, and the important thing is that Whitney showed that just from this information you can reconstruct the graph as long as it is sufficiently connected. And this is a bit surprising because we do not store the information in which cyclic order the edges appear on a cycle. But somehow it's encoded in here and we can reconstruct it. And Whitney also showed
Question, is it implicit in an edge what the vertices are?
No. I mean, you could just, E is just an arbitrary set now. And you completely do not store the information what the vertices are. So if G and H are now finite graphs, then he showed that G and H are planar duals if and only if their cycle matroids are duals. And now dual as matroids, where this matroid dual can be defined completely algebraically, and I'll give you the definition soon.
Now, are G and H planar graphs, or?
And not in the theorem, you do not require that they are planar. But it says they are planar duals if and only if their cycle matroids are duals. So for example, you could even use this theorem to get another characterizations in terms to characterize planar graphs, right? So in particular, this gives you, if you start with a graph and you now look at it, the dual of its cycle matroid, and actually this is not the cycle matroid of some graph, then you originally know that the graph you start with can never ever be planar. Right, okay. Right, so and how is the dual defined? So it's a matroid on the same edge set as the matroid itself, and it consists of those elements x which are minimal and non-empty with the property that they never meet an element of the matroid M just once. Okay, this is a definition, but let's kind of understand what the dual is a little bit better. So we can, if we start with the graph G, then the dual of the cycle matroid is always given by the bond matroid of the graph. And the bond matroid is given by...
Excuse me, but you didn't really define matroid.
I mean, I want to kind of postpone the definition of matroid. First, I want to tell you why they are interesting.
Now, right now you define this for any hypergraph.
Yeah. You define a dual on the same edge
okay.
set.
So we are now talking about hypergraphs.
Yeah.
Yeah, okay.
Right, so you have so now I want to tell you what the bond matroid of a graph is, and it's given by the minimal non-empty cuts of a graph, and a cut is just the set of edges crossing a bipartition of the vertex set. And a cut is minimal non-empty if both these partition sets on the left and right are connected. Then it is minimal non-empty. And a minimal non-empty cut is called a bond. And now the bond matroid of the graph just consists of the collection of all bonds of the graph. I mean, I won't prove you this equality, but just to see that kind of this makes a little bit of sense. Let's now, I mean, if we have some bond, and now we take some cycle, then the cycle has to traverse this bond in an even number of edges because it has to end at the same side where it started, right? So we know that the elements here and here never intersect just in a single element. That's easy to see. But you also have to prove this equality. But that I will skip. Right, so we could now add, I mean, given this equality, we now could add another characterization to Whitney's theorem, namely that this is true if and only if the bond matroid of G is equal to the cycle matroid of the graph H. Right, so this is just because the dual of the cycle matroid of G is just equal to the bond matroid. So we just, by this, get this additional characterization. Right. Okay. So that's about finite graphs. So now let's move to infinite graphs. So what matroids do we have there? So the first matroid is called MFC of G, and it's given by the, again, by the cycles of the graph, which by definition must be finite. And then we also have again the bond matroid, which is given by the finite or infinite bonds of the graph. And then we have a third matroid, which is called the finite bond matroid, which is only given by the finite bonds. Right, and the question we're now interested in is, if we now take the finite cycle matroid of the graph, what is the dual of this matroid?
Sorry,
Yeah.
finite bond, is that just a bond with only finitely many edges?
Yes.
Okay.
And yeah, in this matroid you allow all the bonds, no matter whether they have finitely many or infinitely many edges, and here you just take the subcollection of those which have finitely many edges. Yeah, and later we'll see that they are both matroids, but I just believe me they are. Right, so now we start with the finite cycle matroid of G and want to compute the dual. Right, so if we now just look at the definition of the dual, then probably from a formal point of view, you wouldn't be surprised if I tell you that this may now contain some infinite element. Because you have here some, I mean, you remember that all the cycles are finite, so you have here a bunch of finitary conditions, and then by a compactness argument, you can just build some infinite element satisfying all of these conditions. And actually, this is also true, that actually also happens. So if we just go back to our example, then here in the half grid, we have this infinite bond, which has to meet every cycle, never just once, because actually it's the bond of the graph. So actually we can have some infinite elements in the dual of the finite cycle matroid. I mean, actually you have to check that it's in the dual, but it's not so complicated. And I mean, given this example, perhaps you wouldn't be surprised if I tell you that the dual of the finite cycle matroid of the graph is the bond matroid of the graph. Right? I mean, from the finite theorem, you would expect that it's some type of bond matroid, and it is allowed to have some infinite elements, and actually it is now the bond matroid of the graph.
So you mean you just extended it from finite to arbitrary graphs, that equality?
Yeah. Yeah, and the proof is just the same way. This is true like in the finite case. But I didn't show you the finite proof. Right, and then another thing that's easy to check is that the cycle matroid, the finite cycle matroid of the graph itself, is equal to the finite bond matroid of the dual graph. Okay, so now it seems that we are missing actually something in this diagram, because we have some matroid that is dual to this matroid here and actually equal to this matroid here, and it should be some cycle matroid of the dual graph, but it cannot be the finite cycle matroid of the dual graph, because the finite cycle matroid only contains finite elements, but this matroid contains infinite elements. So there has to be something different in this corner. So to kind of calculate what we have here, let's look at some example. right? Okay, so to construct this graph, we start with the two-way infinite ladder, which you just get by 2 copies of the integers, and then adjoining, adding an edge for all the neighbors, and for each vertex also to its copy. So that would be the graph G. And now we make this whole ladder complete to this new point. So we add lots of edges.
But only on one side. Are those the natural numbers or all?
This is the integers, so it goes infinite to both ways.
You don't put that.
No, how you really should think about this graph is being that you kind of also move this end of the graph kind of near this point, but then it wouldn't be a nice picture to draw on the board, but this is really how you should think about the graph. Right, so now let's draw the dual graph. So we now put a vertex into each face. Then you have all those edges. Right, so that's the dual graph G star. And now let's call this thing we get at the bottom for a moment MTC of G star, and let's see what elements it contains. We know that it's equal to the bond matrix of the original graph, and we know what the bonds of the white graph are. Right, so we now just look if we know consider the bonds. So for example, we have for every vertex just the edges going outside this vertex, right? And they form a cycle in the red graph, right? And in fact, we get all finite cycles this way. But we also get some more sets. So for example, we get all the two-way infinite passes that come somewhere from where both the infinite subpasses go eventually to this side, because this is the bond consisting on one side of the vertices inside and on the other side of the vertices outside. So we get all the double rays that eventually go to the right, and by symmetry we also get all the double rays that eventually go to the left, because it's just a symmetric graph. But we actually get one more, namely the set of all vertices going outside of this vertex is also a bond. And this is now, in the red graph, it consists of two double rays, one going from from here to the other side, and then one going back. So we also get we get all the double rays, all the things consisting of two double rays, where one goes from left to right and the other goes back from right to left. Okay, this looks perhaps a bit complicated, but here's how you should think about it. You should think about it like this. So you do not consider the red graph as a graph, but you consider it as a topological space where you add 2 completion points at infinity. One where all this red stuff on the right converges to, and one where all the red stuff on the left converges to. And now you define cycles just as homeomorphic images of the unit cycle. And then you get precisely these cycles. Right, so let's write this down. So the topological cycle matrix of the graph is given by the topological cycles, which are just homeomorphic images of the unit cycle in the graph together with the ends. Yeah, and I mean, I didn't really define the ends. Just think about them as points you added infinity to the graph. So let's have another example. So if we go back to the half grid, actually you can show that this graph only has one end. So the topological space you're considering for the half grid would be equal to the 1-point compactification of the graph. And then the cycles in this graph, the topological cycle matrix would be given by the finite cycles and the double rays in this graph. Yeah, and these topological cycles were actually invented decades ago for completely independent reasons. But now in return, this matroidal approach gives us now a new approach. So the fact that the finite bond matroid of G is the dual of the topological cycle matroid of the graph. This gives us now a new perspective on
G star.
Thank you very much. Right. So this gives us now a new perspective to the first place where they first invited this.
Shouldn't the star be inside the parentheses? Over there, I mean it's.
No, it's not correct like this.
But there you have the MFB of G star.
Dual. I have dual here.
You do, and you have stars
Oh.
on the graph.
Yeah, but in both sides, right? So that's. I mean, I have. I mean, you have can once compare cycle matroids and topological cycle matroids, and there you have to star in
I
one,
see. Yeah,
and
yeah,
star,
okay.
not star in the other. But if you bond and cycle, then you.
Yeah, now you replace G star with G.
Yeah.
Okay.
Yeah. Sorry, that's perhaps a bit confusing. You're right. Yeah, I suppose I should put an H here.
Yeah.
Right. So this gives now a new perspective on topological infinite graph theory. And there these topological cycles were first introduced. But there are some cases where before you had some complicated topological arguments, but now using this duality you can have now an argument in terms of linear algebra, which is much simpler, and then we just use this duality and kind of get back the old proof. You get back the old result. Okay. Right. So and I mean, but cycles in the original sense are just finite objects. So now if we consider the graph as a limit of its finite subgraphs, then this will eventually contain all the cycles. So this formally means that you can write the finite cycle matroid of a graph as a direct limit of its finite restrictions. Right, and finite restriction just means you take the graph G and delete all but finitely many edges, and yeah, that's a finite restriction. Right, so now if you delete an edge in the graph G itself, then in the dual, what does it mean in the dual? So in the dual, you would have here two faces, and you would merge these two faces. So, and this operation is called contraction. So you can by contracting edge, you identify the two end vertices, and the new edges outside this vertex are the edges going out of one of the two identified vertices. Right. But now if we take some finite contraction of the graph, so now you contract all but finitely many of the edges, and now you take a bigger finite contraction of the graph, then you actually get a projection map from the bigger finite contraction to the smaller one. Where you, if an edge is also, you're just the identity on those edges that are also in the smaller graph, but if you have some edges which are only in the larger graph, then you map them to the vertex to which they get contracted, and similarly on vertices, they always are mapped to a unique vertex to which they get contracted. Right, so you actually have a projection. When you're not considering finite contractions, you actually have a projection map from the bigger ones to the smaller ones. So now if we are interested in a limit of those contractions, we do not have a direct limit, but we have instead an inverse limit. Right, so what we're interested in is the inverse limit of the cycle matroids of H, where H is now a finite contraction of G. Right, and so we're interested in what is now this inverse limit. Right, so let's first check that this inverse limit can contain some infinite elements. Because if you have now a finite cycle in this small contraction, then actually it extends to a bigger cycle in this bigger contraction. And now if you have an even bigger contraction, then this might come from an even bigger cycle and so on. And if you now take the limits of those, this actually might be an infinite cycle. Right, and what actually turns out to be true is that this is equal to the topological cycle matroid of the graph. Right, so here's now the picture I want you to take home from this talk. So now if we have two locally finite dual planar graphs, then the finite cycle matroid of the first graph is the dual of the topological cycle matroid of the second graph. Right? So this we already showed over here, right? Going from here to there. But now this then behaves nice with planar duality, but also with the duality between the direct and inverse limit. In the sense that here we have a direct limit, now we take the dual, and we actually have an inverse limit over there. Right, so what does it mean? So, when we first looked at planar duality for infinite graphs, then we thought maybe it's not so nice as for finite graphs, because what perhaps we hoped was that if we take the cycle matroid of the first graph, then its dual should be the finite cycle matroid of the second graph, the dual graph. But actually, if we now look at it more careful, then it's even nicer. Because now matroid duality behaves not only nicely with planar duality, but also with this duality between the direct limit and the inverse limit. Right, so I hope now I convinced you a little bit that it might be worth, infinite matroids might be worth studying. And now let's define infinite matroids. So an infinite matroid always consists of a ground set E together with a set curly C. I mean, I now give you just one way how we formally could define infinite matroids. And this C is then a subset of the power set of E. So this is a matroid with ground set E. If it satisfies, so the first thing is C1, that the empty set shouldn't be in C, right? So the empty set shouldn't be a cycle. Oh, yeah, thank you very much. So the second thing is that C should be an anti-chain. So for any two C1 and C2 in curly C, we never have that C1 is a proper subset of C2.
Incomparable.
Sorry?
They are incomparable.
Yeah. Right, so the third thing is something like an elimination axiom. So let me first give you the elimination axiom for finite matroids. So there it just says that if you have two elements of curly C which intersect in an edge, then you can actually eliminate this edge, meaning that you find a cycle in all the rest when you remove the edge. And then using this, you can prove inductively that you can actually eliminate any finite collection of cycles. But now, in an infinite matroid, perhaps this is not good enough, because what you want to do at one step already eliminate infinitely many cycles at once. Right? So what is it what you want to do? So let's have a picture here. So you now have some infinite cycle, and you have now lots and lots of cycles with which you want to eliminate, which are allowed to intersect somehow, but not in the edges where you want to eliminate. Yeah, and I mean each of these elimination cycles now has its edge small x and just come from an arbitrary set capital X from this whole cycle. Then you have also some edge z which you fix, and now the elimination axiom tells you that you actually find a new cycle through this edge z which you fixed, which avoids this set x and otherwise uses only elements from the cycle C, these new cycles, but not from the set x. I mean, this is now a bit complicated to write. Let me write it down, but I mean, really just kind of keep this picture in mind. So for every C in curly C, and for every Z in C, for any X subset C, and for any collection of cycles Cx, where X is in X, and these Cx's are in curly C, there actually exists some C primed in curly C, which contain, so that's this green thing, which contains the edge Z, and otherwise is contained in C together with the union of all small x and big X of the Cx without the set X. And yeah, I mean, here I forgot one condition. So we also have to make, I mean, I told you that they only are, in the small x's they are disjoint. So we have also that X is in Cy if and only if X is equal to Y. Right, okay, but this is now really formally the elimination axiom.
That should lie on a new put this here.
Sorry, yeah. Thank you. right? So then we have one last axiom, which is a bit, again, a little technical, but kind of roughly what it says is just that bases exist. So bases are just maximal sets that do not contain a cycle. And if the matroid is finite, then obviously such set exists. But if now the matroid is infinite, then really we have to make it an axiom that they exist. Right, so yeah, so let me again formally give you what it says. So now we do not only need that bases exist, but also bases exist in various situations. So we now have a slightly more complicated technical statement, but it really just is this. So we have now some for any I subset X subset E, right? And now just think about I being the empty set, X being the whole set, and then this just says that bases exist, but it's a slightly more general. Right, so we have here our I, here our set X. Right. And this now says that there exists some J maximal with I is a subset of J, subset of X. So the J lies somewhere between here. And so it's like a base containing I, but contained in X. So kind of, or think about it as a yeah. And now we have the property such that for every C in curly C with C is a subset of J, we already know that C is a subset of I. Right? I mean, just think about it, what it means when I is the empty set and E is the whole set, and just means that J does not contain any cycle. So it should be maximal independent set. Right. So these are infinite matroids. So let me give you a quick historic background. Right, so while matroids are introduced in the 1930s, infinite matroids in this way were first defined by Higgs in the 1960s, but at this time it was not really clear what infinite matroids could be good for, and even such simple axiomatizations of infinite matroids were not known. But then, yeah, then they were further studied by Oxley, but only recently in 2011 there were kind of axioms for infinite matroids so that you really could work with them. Right, so axioms in terms of circuits, as I gave them here, independent sets, so which are just sets that do not contain a circuit, bases, which are maximal independent sets, or also in terms of ranks, or also in terms of closure, and this is how Jurek yesterday defined matroids. So, so the closure of a set X is just the set of all. Yeah. So the set of all E such that there exists some C in curly C with C without E is a subset of X. So this is the closure of an edge set, and you could also define
Together with X.
yeah, you're right. Yes. Thank you. Right, so this is the closure of an X. So you could now describe closure in terms of circuits, but you also can have axioms which are just in formulated in terms of this closure operator, which also axiomatize infinite matroids.
It's not clear that this is a closure operator, but you should follow them from the axiom.
Yeah, and then you have these closure operator axioms, with also, and from them you can also prove these axioms and so on. Right, and this was done by Henning Bruhn, Reinhard Distel, Matthias Grisel, Rudi Pendevin, and Paul Woolen. Right, so, and since then, Nathan Bowler and I had kind of started the systematic study of infinite matroids, and we are particularly interested in the matroid dissection conjecture. And yeah, in Nathan's talk you will hear more about that. Right. Yeah, and I also should tell you, so the first part of the talk, and this was not really things that I proved, but it's rather a contemporary explanation of things that others did, like Henning Bruhn, Reinhard Distel, or Carmesin. Right. Okay. Okay. So that's all right. And I should also tell you, right. So this now the study of infinite matroids is quite new. And at the end of the talk, I want to give you some open problems which have, I think, a very set theoretic flavor. Right. Okay. So now we define infinite matroids. So let's sum up some examples we already have. So we have the finite cycle matroid of the graph. So why is it a matroid? Well, all the elements are finite, so the elimination axiom is kind of just trivially true because you just have to prove the finite axiom, and this is true by the same reason as for finite matroids. And then you have to prove that bases exist, maximal independent sets not containing a cycle. But this is, again, very easy because all the cycles are finite, so you could just use a standard Zorn's argument to actually get that this is a matroid. So there is not really an infinite reason why this is a matroid. And yeah, and similarly, of course, we have the finite bond matroid of the graph. And then we also have the bond matroid of the graph. And how do you prove that this is a matroid? Well, we said that this is the dual of the finite cycle matroid. So you prove once and for all that the dual of a matroid is again a matroid, and then you also know that this is a matroid. So to give you some other example, so we now take E, a set of vectors.
Excuse me,
Yeah.
have you defined the dual of a matroid?
Yeah, it's precisely defined like this. Yeah, just this definition.
Yeah.
No matter whether the matrix is finite or infinite.
Yeah, that makes sense for any hypergraph.
Yeah. Right, so E is now a set of vectors in a vector space, an arbitrary vector space. And you say that now curly C consists of the linear dependencies, so consists, to be precise, of the supports of linear dependencies which are non-empty and minimal with this property. And again,
What is the support?
so you now take a linear dependence in this vector space. I mean, you have now a set E of vectors in the vector space.
Yes.
And now you know when they are linearly dependent or not. And
Yeah.
now you just take the set of those vectors, the set of those vectors that appear in the linear dependence, and you now consider those that are non-empty and are minimal with being a
But what is
dependence.
support? I don't know. Support, I don't
Support of a linear
understand.
dependence is the vectors that appear in it.
Yeah,
non-zero.
some
Yeah.
sets that are linear. Oh,
Yeah,
yeah.
it's just how
Never heard this
you could.
before. Yeah, I heard, but
Yeah.
not in this.
Yeah, it's totally too complicated way to say it. Right. Okay. Right. Right. So but we also have we also looked at the topological cycle matroid for a locally finite graph G, and there we said that it's equal to the finite bond matroid of the graph G. But this is only true if the graph is locally finite. So if G is not locally finite, then actually this is no longer true. And just to give you some example, so you can say you
Totally finite is that all points have finite degree.
Yes.
Right?
So every vertex has only finitely many neighbors. So you could now, for example, to take some complete graphs on a lot of vertices, say on Aleph 1 many vertices, and glue them together in a binary tree shape. But glue them together on finite separators in a binary tree shape, and then actually you can check that this graph does not have any finite bond at all. So this matroid is completely trivial. But this graph has lots of ends, namely one for every one for every branch of the infinite binary tree. And it has lots of interesting topological cycles, which are given by, for example, like this, or you could also have more complicated ones, which go somehow like this, and so on. So you have lots of topological cycles. So actually, the cycles are very interesting. But also in the dual, so if you, for example, look at all the edges incident with the vertex, this actually you can show as a cycle in the dual matroid. So also the dual has no some infinite elements, right? So the reason why this is a matroid is not just that all cycles are finite, and it's also not just that in the dual all cycles are finite, but it's more complicated. But actually, let me just tell you right now, and that actually that this topological cycle matroid is a matroid for every graph, right? But you can no longer use this equality here, and you also cannot use something similar because you can always prove that this matroid here is basically countable. I mean, it may have an uncountable ground set, but most edges will just be in parallel to some other edges, right? And then kind of, yeah. So so to make it precise, this matroid is always isomorphic to a matroid of a graph with only countably graph with only countably many vertices, but where you allow several edges joining the same pair of vertices. So this is kind of not interesting for uncountable graphs, but this is really interesting, and also the reason why it is a matroid is interesting. All right, so let me explain this a bit more. Right, so when we believe that this is a matroid, actually we know that this thing has some bases. So how do the bases look like in this case? So a typical example of a base, so maximal set with the property doesn't contain a circuit, so in a graph it's just a spanning tree. And so here an example of a spanning tree would look like this, that you have basically the binary tree and then have lots of edges sticking out at each vertex to kind of collect all the other vertices of the KL of ones, right? So how usually bases look like are you have spanning trees and sending one infinite path to every end of the graph. Right? So this way you ensure that it does not contain any circuits. And these spanning trees are called end-faithful spanning trees. And in infinite graph theory, for quite some time, it was not known whether every graph has such an end-faithful spanning tree or not. And Harding conjectured that every graph, every connected graph, of course, has an end-faithful spanning tree. So such a spanning tree which sends precisely one infinite path starting at the root to every end. And he proved this for countable graphs, but really the problem about this conjecture is what happens if the graph gets uncountable. Right, and then I should also mention that in his original version of the conjecture, Harding uses only slightly the wrong notion of end. And so there were some counter examples against this conjecture in the 1990s by Robertson and Seymour, and independently by Carsten Thomason. But if you use the right notion of end, so as we're doing this talk, so just take the topological notion of end here, then actually this is true. And the reason why this is true is very related to the reason why you actually get a matroid here. So the proof is very similar. And I already mentioned what the connection is, right? Because bases of these matroids are very similar to kind of these end-faithful spanning trees. Right, so So now I promise that there will be some open problems. Yeah. Okay, right. Right, so very simple finite matroid is a, can you all see it? Is a uniform matroid. So this is one where you have some number k, and the circuits are precisely the sets of size k. And here's a way how you can define uniform matroids for infinite matroids. So a infinite matroid is uniform if for every set C, if you take a k element set inside the set and a k element outside the set, you can swap it and you again have a circuit. So it's kind of having this. Okay, so right. So first I should tell you some. Okay, so what are infinite uniform matroids? So a trivial way to define them now would to say, you take your some cardinality and the circuits are all sets of that cardinality. And if the cardinality is finite, then actually this makes sense. But now if the cardinality is infinite, I mean you want to have some maximal independent sets, right? But this kind of then completely breaks, right?
An anti-chain.
Yeah.
C2.
Yeah. So this completely doesn't make sense. So, but we can repair it by just requiring this uniformity properly locally at each circuit. So if you start with a circuit and you kind of can always replace it by finitely many elements, but not by infinitely many elements. So this way you get an interesting definition of infinite uniform matroids. But now it's very hard to construct them. So now if you want to get an infinite matroid, uniform matroid with an infinite base and infinite cobase, it's not really clear why they should exist. But actually Nathan Bowler together with Stefan Geschke proved that they exist if you assume Martin's axiom. But it's not clear, it's not clear whether you get them in ZFC or what the consistency of that is, and yeah. So it's I think, a very set theoretic question that arose in infinite matroids. Right, so let me just mention one more question. So, so an infinite matroid is tame if the intersection of every circuit of the matroid with every circuit of the dual matroid is finite. And kind of studying infinite matroid, this was a property that arose all over the way, and most infinite matroids are tame, which are interesting from kind of the combinatorial study. And then we proved that actually the tame matroids have a very interesting axiomatization, namely one where you can basically get rid of this axiom that bases exist. So you just take these circuit axioms, roughly, and the circuit axioms for the dual, and then you can actually prove some axiom like the bases exist, but you do not have any axiom that tells you some maximal sets exist, right? So and this is, of course, very helpful when you want to prove that something is a matroid, because you do not have to prove the most complicated axiom. But this only works if you have a countable ground set. But if you have an uncountable ground set, the proof completely breaks. And again, when you get uncountable, it starts things to get really interesting. And I hope, it feels again very set theoretic. I don't know what the real proof is, but I think complications that arise there look set theoretic. And so I would like to ask you the question whether we could actually drop the assumption whether it's countable. Yeah. So thank you very much.
So, any more questions or comments for Johannes? Well, can I ask, you mentioned a result using Martin's axiom for that question 1 there. Could you say a little bit more about that? I mean...
Yeah, so so you now have to prove that actually you get a matroid, right? So you have to prove now that you satisfy these axioms, and the idea is first, yes, so how long should I, like 5 minutes, is it okay?
If there are no other questions, I guess you could go that long, but maybe just a sketch overview, very briefly.
Right, okay, so very briefly, it's I mean, you have now to check all these axioms, right? And, okay, so the way you're constructing it, you just put in one circuit, and then you put in all the circuits which you get for the uniformity property. So you kind of take in finely many elements, and you replace them by finely many elements inside of the same size. But if you do it this way, you already get.
Excuse me, what is the exact statement that you are proving?
Wait, so this zero momentum.
What exists?
Right, so,
A matroid or uniform matroid of what size?
so the theorem is of Nathan and Stefan is that there exists, so assuming Martin's axiom or continuum hypothesis, whatever you like, that there exists a uniform matroid M such that there exists some C and M with C is infinite and also the complement of C is infinite. And you actually can get this on a countable ground set.
So it's on a countable
Yeah.
ground set, on omega.
Yeah. Right, and the idea is kind of, to put in the base.
Okay, at least now we have a statement. Because
Right, and the question is.
earlier you didn't specify really.
Okay, so the question is, can you just leave out this, right?
We understand that's the problem. But what was the statement wasn't clear. Okay, now it is.
Right, any other questions or comments? If not, let's thank Johannes again. Now we have afternoon tea for